Hello everyone, Aaron here. Welcome back to Leetcode, and today we are doing another binary search tree problem. We are tackling the binary search tree iterator puzzle. So the point of this problem is we want to implement a class. Sure, we're in C. Implement the BST iterator class that represents an iterator over the in-order traversal of a binary search tree. So an iterator is meant to be this sort of lazy structure, effectively. It lets you walk over a data structure in some predefined way, but it doesn't just do it immediately in one go. You have to specifically say, all right, now I want to go to the next thing. Now I want to go to the next thing. So some languages like Python have extensive built-in support for this, and others like C have almost none. So it's kind of a standard setup here. You have to create it. Then there's a has next, which tells you whether you can keep going, and then there's a next, which will tell you what the next thing in the iterator should be. Notice that by initializing the pointer to a non-existent smallest number, the first call to next will return the smallest element in the BST. I'm curious as to why it's specifying what we have to do to manage the pointers, because that feels like an implementation detail that the specification should not be giving us. All I should be told is that I have to have a way to create it, a has next, and a next. Very strange. Anyway, I think doing this in C would be educational. And then afterwards what we'll do is perhaps we'll go back into it in Python just to sort of show the vast differences that there are between these two setups, and how much easier a language like Python makes it to build an iterator. We have an empty BST iterator struct. We'll need to fill that in with the state we want to maintain. Here's our creator. Here's our next stepper. Here's our check for whether it has the next thing. And because we're in C, we need to free the memory after we've finished using it. It's a wee bit unclear. No, well, okay. We should not free the tree because we are not the owners of the tree. We just need to free the state that we are holding. Right. The actual approach that I want to take for this problem, I think I want to lift an idea from functional programming here. And this is the idea of a zipper. Now, if you've not seen a zipper before, basically it's just a way of moving through data structures without having to do a whole lot of weird thing. It's a way of moving through data structures. So for example, if we had a list 1, 2, 3, 4, 5, the zipper would initially look like this. It would say, well, I've got nothing to the right, and I've got the rest of the list to the left. And then as we move along, we would end up with something like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And you can see what it's doing is it's not only moving us through the list, but it's helping us remember what's in the past as well. And this makes traversing these kind of structures quite easy. And basically we're going to take this idea from, instead of applying it to a list, we're going to apply it to a tree. So what we want to do is we kind of want to have a it's a tree struct tree node head, and then we also want to have a that is meant to be a semicolon, and we also want to have a struct tree node maintaining all of the things that we've passed effectively. So if we're here at the 3, for example, the head is the 3, and the past is the 7 and everything on this other side that we didn't take. If we're at the 15, the head is obviously the 15, the past is the 7 and everything we didn't take. If we're at the 20, this is where it gets a bit different. The head is obviously the 20, the past is the 15, and on one side the child is the 9, and on the other side the child is the 7. Actually, so we need to work out how we're going to decide which direction we went, because these two children don't really, well, one is the parent and one is the child we didn't take. So what we really want is a history node which we'll call the context, and the history node, what that contains is sort of the value that was being held there, struct tree node, other path, struct tree node, no, not a tree node, so we've got the other path, and we've also got the rest of the history that we're interested in. And here we need our bool saying whether we went left. So the other path, if it's true we went left, if it's false we went right. Whatever. I think these two things are enough to get us going. So the thing we want to do is we want to create our iterator. So first we're just going to malloc the space for it. Oops, that's a pointer. The head is going to be the root. And the context is going to start off at nothing. There is no context. Then what we want to do, how do I want to do this? Now let me just think for a second. Because this is all the state we need at any given step. To go to the next state, basically all we want to do is walk as far, wherever we're at, we want to go left as far as we can, and if we can't go left, we want to return the value. Okay. So we've got a few cases here. If the head left is null and the head right is null, then we need to walk back up if the right is null, if the left is null and the right is not null, so here we can't go that way, but we can go that way, then step right on the object, actually, you know what? I think I'm going to remove all of this logic and just going to create. No, what do I want to do? I have in my head this rough picture of what I want to happen, but I'm not 100% sure how to make it happen. So on the first call to BST iterator next, in fact, I think what I want to do is always just have, what I want to do is I want to arrange this slightly differently. I want to always be looking at the next thing. We'll assume we're only going to be called if we're allowed. Yeah, you may assume the next calls will always be valid. So what I want to do is I want to get obj head val next obj. In fact, you know what? They've used obj everywhere here, so I'm going to use obj up here. And then return val. Has next, this would be return obj head. It does not equal null. Probably doesn't need parentheses, but I like having it in parentheses. I'll worry about the free in a minute. In fact, no, let's worry about the free now, because what we've got is we don't need to free the head because the head is something we were given. So it's going to be, well, at the end it's going to be free obj. But the thing is, here we want to free the history nodes. As well. So let's do free history. Now, the only ones we don't care about freeing the tree nodes because, again, they were things that were given to us. We're only interested in freeing the history nodes. So this is a struct history node. History. Typing. This is effectively a linked list in the history. So all we have to do is free this like we would a linked list. So while cur is not null. What I want to do is I want to take struct street node start. Next is parent. I want to free current. And I want to do current is equal to next. So this will effectively just walk our way back up, trying to free everything in the history. So now that leaves us with effectively just one thing to define, which is next. Void next, and this is the BST iterator ob. And this one here I'm going to allow to be fully recursive. So if obj head left now hang on, I've got to be a bit careful here because I want to walk that way, but when I get back up to the 7 I don't want to try and immediately go to the 3. So this isn't entirely safe, because if I get back to the 7, don't want to be rushing down the 3 again. Maybe there's an easier way to maintain this. Rather than taking inspiration from zippers, perhaps we can just maintain a stack that has the parent and whether we just went left or right. That might be easier to maintain. So the history node here would actually just be, it would literally be a linked list. So here, if we're looking at the next thing, so if the left is not null, no, hang on, before I go and make changes. All right, hang on. So let's say the head is currently here and the context is empty. That can either be because we've just started, or we're literally this far in our traversal. Well, that's no bloody help, is it? Another way to think about this is we want to mimic the call stack, but we want to do it in such a way that we can kind of pause at any given point. And at any given point, the call stack has to kind of know where it's up to. Well, that's kind of what we're mimicking here. I'm just struggling to turn that into code. So if we're here, every node gets visited twice. The first time as we're walking past it, the second time as we come back. Yeah. So we have a visited node. So if we can go left and we've never visited this node, then what we want to do is we're going to set object visited. No, that's not quite right, is it? Gosh, this is another hard one today. I don't actually think I want that there. Let's have two bools, one for visited, one for went left. No, that's not right either. So I'm just trying to think. When the iterator is pointing at the 7, maybe I'm thinking about this in much too functional programming a way. How would a C programmer think about this? If we go here, we need to remember a pointer up to here. So we always need to remember the parent. We need to do that recursively. And we also need to remember which direction we went. The history node. The head holds that, then the history node holds the value of the parent. Why doesn't it just hold the parent, more history, so when we get here, we know our parent. Hang on. Let's look at this another way. If I'm holding onto my parent, and I also need to know how many times I visited the parent. I visited it once, it was on coming down. I visited it twice, it was coming back. Let's call it visited. Still. Does that actually help us with the problem of how do I know when I got here? Not really. If I go next, all the way down to here, then when I call next again, it needs to walk up the history and just stop. Let's try this. Hang on. So if I'm looking at a node, if the left is not null and the next direction is to go left, what I want to do is effectively go down yeah, so I want to create struct history node previous is malloc size of struct history node. I want to make prev. I don't think I need visited anymore. Prev.parent is equal to object head. That's where I currently am. And previous history is whatever's currently in the history. In the context, sorry. Else if obj next direction, hang on. So we were saying to go left. Here, if the next direction is right, if I can go right, obj next direction is equal to right, then let's do another one here. Center, just so I can fully keep track of what's going on. So so just to mirror the structure of an in-order traversal, if obj next direction is equal to center, well, in that case, I don't actually want to go anywhere because this is just moving. See, I don't even know if I want that. So I'm at the 7. The next direction is left. I want to go to 3. I'm at the 3. Left is equal to null. So else if obj head left is null and obj next direction is left, then hang on. Hang on, I didn't finish the previous one. Obj head is obj head left, ob context is prev. And then I want to keep going next. Obj. No, this isn't going to work, is it? No, it is going to work. I always want left as far as I can. So that one's allowed to be eager. It's then if I've walked left as far as I can, there's nowhere left to go. That's when I want to stop and I want to say the next direction is going to be right, but I want to stop there. And then after that's been dealt with, they're going to come back. If obj head right is not equal to null, and obj next direction is equal to right, I'll do something else. If obj head right is equal to null, and obj next direction is equal to right. So this is the case where I want to walk back up. So here it's going to be obj head is actually equal to obj context parent, and obj next direction is equal to right. Because I've now walked back up to there. And also obj context is obj context history. Because we're stepping up by one. So then this leaves us with the case where so we'll come back up here, and then we'll deal with the 7, then we call next. And then, so if we're here and want to go next, that means we want to go right. We can go right. So it's we want to create a history node again. Parent is going to be what we're currently looking at. Previous history is going to be context. The head is going to be obj head right. Obj context equals previous, and here I also want to make sure obj next direction is left, because when I get here I want to keep going, and then I actually want to call next again because I need to dig as far left as I can. Okay, that's a bit more complicated than I had expected. Is my free still correct? So it's currently focused on something. Hang on, is there a case I've missed here? Yeah, I think there is. If we get to here, so we walked here and we stopped because we couldn't go left any further. The next direction is going to be right. Oh gosh, okay, I think we just need to run this through in our heads completely. So we create a new iterator object. The head is here, the context is nothing, the next direction is next, and we call next direction is left, and we call next. Now next says, if I can go left and I meant to go left, create some history that says, well, here is your history. The head goes down on the left, and I call next again. I'm meant to go left, but I can't. I'm going to say the next direction is right. Stop. I'm looking at 3. So has next is going to be true. And when I call next, I get the value of it, and then I move the pointer along. So I call next. So the next here says I should go right. Right is the next direction, but there is no right to go. So the head is this. The next direction I need to go is right. And I move up the context, but I've stopped here. So then the next thing can be a 7, that's fine, and I call next. The next thing I need to do is go right. So I can go right, right is not null, so I create some history that puts that in there. I set the next direction to equal to left, and then I recurse down. It says if I'm going left and left is not null, go left. Great, I'm in here. It says go left, but left is null, the next direction is right, but I stop. So I'm looking at the 9. The next direction, so I'm asked for next again. I'm told you need to go right. I can't go right, so I step back up. Hang on. I need to go right. I can't go right. So right is equal to null. Head up. Next direction is right. And I stop. Here I'm told I need to go right. I can go right. So I go right. I create some history that puts it there. Go down here. I'm told I need to go left. Can't go left. So I set the next direction to be right and I stop. Then I'm told next again. I need to go right, but I can't go right. So I step up. I'm told I need to go right and I stop. Now I'm walking back up the tree again. How do I stop this going up here? Basically, in the history, I just need to maintain whether it's been seen or not. If I'm going left, previous seen is equal to false. But if I'm going right, previous seen is going to be equal to true. And then here when I pop up, if obj context seen head is null. So that should be enough then just to immediately stop everything. Because that will signal to our this thing here that the iterator is exhausted effectively. Whew. So that will mean if we're trying to, so yeah, this is the right case. We're trying to go right, but we can't go right. If this thing up here was marked as seen, and it gets marked as seen if we are trying to walk, if we're trying to go right from it, then we're done. Okay. By some miracle, I think that works. Let's test it and see what happens. I'm not super confident. Unexpected. Oh my goodness, line 16. Expected. Oh. Forgot the semicolon after my struct. That goes to show you how much I'm using these. Ugh. Free. Oh, that's because I swapped these names, didn't I? That's a good check. I never actually use center anymore. So these ints could actually just be a bool, but eh. And then I've got no thing. Oh, that's because it's called context. Oh boy, I did not check this very carefully, did I? Terrible. No wonder my confidence is low. Which is end of. Whoops. Didn't actually return anything. Ah, but once we saw the little syntax errors, we actually got it right. I've only given us one example here, so that's. We're flying a wee bit blind. Nervous. Alright, just click it. Sorry. Member access with null pointer type of struct history node. Has next. Next. Has next. How do we get into this condition? So the tree is just a single leaf. If obj context is no, oh, I see. So the case here was we're at the top of the tree and we're asking to go next, and I'm checking, well, I can't go right. Have I seen what the parent is? Obviously there's no parent. So that's an equally valid condition in which to stop. So I've inserted the one we failed on in here. Test cases, incorrect number of arguments expected 2 got 1. Well, I've got to take both lines. So this is the test case we failed. Now we are passing it. Another one we failed. There must be a few edge cases that we have not thought of. So what's going on here? Line 75. Has next, has next. Somehow the head has become. Oh, now we're stopping too early, I guess. This is a 3, 1, 4. Oh, I can never read this damn tree notation. 3, 1, 4, null, 2. What does that even look like? I think that's a 3, 1, 4. Null 2. So that looks like 3, 1, 4, 2. So the problem we're getting here, so 3, go left as far as we can, and then we stop. Yep. We're told the next thing to do is go right. That's fine. We go here. We stop. So this check here must be causing problems. If we cannot go right, we're told to go right, and there is no context, how on earth would that happen? Oh, it's an or. If there's no, hang on, if we're told to go right, and if we're told to go right, there's no right, and there's no context. Well, that's none of those cases. Anyway, line 75. Iterator next. Somehow we have decided obj head is not equal to null, and yet I'm very confused. 1, 2, 3, 4. Has next. Head is not null. That's because we made it all the way to the 1. Let's print it out and see what's going on. Line 90. Oh. You're a problem. Right. One, 2. It's the 3 it's struggling with. We've gone up here. So we were at the 1. We were told to go right. Hang on. So we were at the 2. We were told to go right, and there was no right to go down. There was context. So we go to the... Huh. How did that work previously? We just never hit this case before. Apparently we've never hit this case before. So we were told to go right, but there was no right to go. So we want to step back up 1. And in fact, if we were told to go right, and if we were told to go right, and there's no right to go down, so we're here, we want to step back up 1. Here we were told to go right. We need to recurse here a wee bit, don't we? Because here we're looking at the 1. We're told to go right, we can go right. But We've seen it before. We don't want to set it to null yet. Next, obj. So actually, if obj context is equal to null, so here if we're stepping up, this is the condition where we want to bail out. Else, if the object context is seen, hang on, no, that's not right. Yeah, if we're told to go right, and we can go right, this condition needs to be up here. If object context is not null and object context seen, oh, hang on. No, that. Hang on, I'm getting myself confused. So, I'm at the 2. This has been seen, unfortunately. So what we need to do is we actually need to keep walking up until we hit something that hasn't been seen. So we'll do an else here. So while we've got an object context seen, and in fact this is what we want to do. In fact, we always want to take one step up. So do I want to make this a do loop? Right. So let me bring up this little example a bit further. So we're at the 2. We can't go right, but we've been told to go right. There is context. So what we want to do is go up here. No, I'm going to get myself tied up in knots. Scene parent. While scene parent object context will make the context the history. So we're here, this is the context here. If we've seen it, This is it. We haven't seen it. Great. So what we want to do now is we want to go obj head is obj context parent obj context history obj next direction is right. I think that's implied anyway. All right, what does that do? How badly have I completely broken this logic? Badly. So while obj context, so if we keep stepping up, why am I going 3, 9, 20? What happened to the 7? Oh, I don't need that call anymore. In fact, let's put this here. This all lines up like this. Okay. While there's context and the context can be seen, keep going up. There's no context anymore, so we've stopped. If the context is null, obj head is equal to null. We've run out of places to jump. Otherwise, there was still context. So if we got to here, hang on, let's go to our example. So we got here, here's our context now. This is the context that we're looking at. So obj head is going to be this. Context is going to be null. The next direction is going to be right. I think that works. Okay, that's all of those cases. Let's try again. Oh, I'm still printing. But they don't care. Let me just remove it though for my own sanity. It will use a little bit less time, teeny tiny. We're not terribly fast. We're faster than 40%. I suspect we're kind of middle of the pack. Memory usage is also kind of middle of the pack. Nothing amazing. That was a bit of a hard one. It's really this case here that's the problem. Now, am I storing too much in any particular place? Maybe I am. It's not too bad. Now, I think I promised I would have a go at doing the same thing in Python. So let's go in here and see how it works. Class BST iterator self root. Okay, so self.root equals root. Let's do the iterator is equals of the tree is if tree dot left yield from iterator tree.left yield tree.val if tree.right yield from iterator tree.right. In fact, I don't even need to store that. So it's going to be the next of self.iterator. Has next is I don't actually know how to do this in Python. How do you check next? Okay, we might have to be a little bit clever here. Self.next val is next self.iter. Then we'll do result is self.next val. Self.next val is next self.iterator. And then return result. And then finally, if self.next val should we better guard this and it'll try. Except, oh goodness, what's it called? Stop iteration, I think. None. And we want to do exactly the same thing here. If self.next return bool self.next val. Let's have a quick looky see. That looks good. Submit it. Wrong answer for one of them. Ooh. Why? Oh, the zero. If there's zeros in it, that's going to cause me all sorts of trouble. Return self.nextVal is not none. Blech. I shouldn't have been lazy. There we go. Much, much slower. But it's, what, 30 lines? Our C version was, got nearly 100 lines. And it's significantly easier to understand. It fits on a single screen. We've used all of Python's built-in stuff and it took us a few minutes compared to, I'd hate to think how long I've been going, like an hour for the C version. Right. After that marathon, I think I'm going to leave it there. Thank you very much for watching, and I will see you all tomorrow. Bye. The vast differences